Have you ever thought about the connections between Earth and space? I mean, the stuff we don't usually see.
Right, like the constant energy flow from the sun.
Exactly. How it interacts with our atmosphere, creating, auroras, but also these really powerful currents.
Huge amounts of energy moving around up there.
So today we're doing a deep dive into a NASA mission that's looking right at that. It's called EZE.
The Electrojet Zeeman Imaging Explorer. Bit of a mouthful.
Yeah. But it just hit this big milestone, first light. It saw what it was designed to see for the first time.
Which means it's ready to start unlocking some secrets.
Totally. So our plan is to unpack what EZE is, how it works, the science behind it, and why it's actually really important.
Yeah, why understanding these currents matters for space weather and protecting us down here.
And we're basing this on NASA's own announcement. NASA's EZE mission captures first light and some of their other info. Ready to jump in?
Let's do it.
Okay, so EZE's Electrojet Zeeman Imaging Explorer, what's its main job?
Its primary goal, really, is to get detailed information about something called the Auroral Electrojets.
Auroral Electrojets. Okay, break that down.
Sure. They're these intense electric currents. They flow way up in our atmosphere.
Right
where the auroras happen, the northern and southern lights, about 65 miles, maybe 105 kilometers up.
So like electric rivers flowing through the aurora.
Kind of, yeah. They get formed when a huge amount of energy from the solar wind gets dumped into our upper atmosphere.
And that dumping of energy also causes the auroras themselves.
Precisely. It's the same mechanism. The energy excites the atmospheric gases, making them glow, and it also drives these massive currents.
Wow. Okay, so it's not just about pretty lights then. Why do we need to understand these electrojets so badly? What's the so what?
Well, it's fundamental to understanding Earth's whole connection to space,
Sure.
How our planet responds to what the sun throws at it.
And space weather impacts.
Exactly. These currents are a key part of space weather. Understanding them helps us figure out how to mitigate the negative effect on our technology, our power grids, satellites, communications, all that stuff.
Could EZIE's data help answer questions we just, couldn't even tackle before, beyond just protecting stuff?
Oh, absolutely. Before, we mostly got snapshots, right? A satellite flies through, takes a measurement. EZIE gives us maps, continuous maps.
So you see how it changes over time, the dynamic?
Exactly. How quickly does that solar wind energy get deposited? How widespread is it? That dynamic picture is crucial for refining our models of how this whole system works. And the mission, it launched back in mid-March.
Right.
And these first light measurements we mentioned, they basically just confirmed the instruments are working perfectly. It's really poised for discovery now.
Okay, let's talk about the how. How does it actually get these measurements? You said it's satellites.
Right. It's actually a team, a trio of CubeSats.
CubeSats, so small, sort of standardized satellites.
Yep.
Really changed the game for getting missions up quickly and relatively affordably. These three are specifically designed to map the strength and also the direction of these electrojet currents.
Up close and in detail.
That's the plan. For the first time, really, with this kind of comprehensive mapping.
Why three, though? Why not just one bigger satellite? Does having three give you a better angle or something?
It gives you multiple viewpoints simultaneously. Think of it like triangulation.
Okay.
With three, you can pin down the location and the structure, the sort of 3D shape and extent of these currents, much more accurately than you could with just one pass.
So you see how they evolve in space, not just time.
Exactly. It gives you that spatial structure.
Yeah.
And the really clever part, the really innovative method is how they measure it. They don't fly through the current. No, they actually look below it. They study emissions coming from oxygen molecules about 10 miles or 16 kilometers underneath the electrojets. Okay, wait. Why look below? Wouldn't it be easier to measure the thing itself? And isn't there, other stuff in the atmosphere that could interfere?
Great questions. They look below because these oxygen molecules at that specific altitude emit microwaves at a very particular frequency, 118 gigahertz.
A specific fingerprint.
Exactly. A very clean signal. And the atmosphere at that frequency is quite transparent, so you get a clear view. Now, the magic happens because of something called the Zeeman effect, or Zeeman splitting.
Okay, I've heard of that in, physics class, maybe.
Yeah, it's a fundamental physics principle. Basically, when there's a magnetic field present...
Like the one from the Electrojet.
Precisely. That magnetic field causes the 118 gigahertz emission line from the oxygen to split into multiple components. It literally divides the signal.
Okay.
And the amount of splitting, how far apart those components are, tells you the strength of the magnetic field.
Ah, so stronger field, wider split.
You got it. And not just the strength. By looking at the polarization of those microwaves, sort of the orientation of the waves, you can figure out the direction of the magnetic field too. So you get the whole vector.
Wow. That's really elegant. So you're using oxygen molecules as remote sensors for the current above them.
Essentially, yes. And this isn't just, a theoretical idea anymore. Applying it this way, at this frequency, remotely, is the breakthrough. It's like giving us a remote scan of the Electrojet's magnetic signature.
And the instrument doing this is the MEM.
Right. The Microwave Electrojet Magnetogram. There's one on each of the 3 CubeSats.
So March 19th, 2025, that was the day. The first successful detection of this Zeeman splitting.
That was the day. One of the satellites, using its MEM instrument, recorded that split in the 118 gigahertz oxygen line. Proof positive.
What was the feeling like for the team? Must have been huge relief, right? Or just pure excitement?
Oh, absolutely. Huge validation. Years of work coming together. In that first measurement, they were actually looking near the magnetic equator, and they saw the splitting caused by Earth's own magnetic field.
So it proved the instrument could detect magnetic fields accurately.
Exactly. Sam Yu, who's the principal investigator from Johns Hopkins Applied Physics Lab, APL,
Right.
He said, basically, the observations show everything's working just as they expected. Spacecraft, instrument, all green. It's a massive hurdle cleared.
So the system works. What happens next? When do they start the real science?
Well, now that they have this first light confirmation, they spend about the next month or so doing final checkouts, calibrations, making sure everything is tuned perfectly.
Dotting the I's and crossing the T's.
Pretty much. And then after that, they switch over to the formal science phase. That's when the continuous mapping of the Auroral Electrojets really begins. Data should start flowing soon.
And putting this into the bigger picture at NASA, this isn't just some isolated experiment, right? It fits into their broader goals.
Oh, definitely. It's funded by NASA's Heliophysics division.
Heliophysics, understanding the sun and its effects.
Exactly. How the sun influences the entire solar system, including Earth. So EZIE feeds directly into that understanding, that sun-Earth connection.
And specifically the space weather aspect.
Yes. It connects strongly to other NASA missions trying to predict solar storms, understand their severity. Knowing how energy flows into the Electrojets is a key piece of that puzzle.
Which is becoming more and more critical.
Absolutely. Think about things like the Radiant Program research and development of initiatives of advanced new technologies. NASA is constantly pushing the envelope on this research.
And making a mission like EZE happen, it involves quite a few players, doesn't it? It's not just NASA HQ.
No, it's a real team effort. You've got the Johns Hopkins Applied Physics Lab, APL, leading the mission science-wise.
Okay.
Then Blue Canyon Technologies, they actually built the CubeSat buses, the platforms.
Right.
NASA's Jet Propulsion Laboratory, JPL, built the crucial MEM instruments.
Ah, JPL built the eyes.
You could say that, yeah. And the whole thing is managed by the Explorers Program Office over at NASA Godier.
It really shows how specialized space exploration has become, needing all these different expert groups to pull off something like this.
It absolutely does. You need the science vision, the engineering know-how for small sats, the precision instrument builders, the program management. It's complex, but that collaboration is how you achieve these breakthroughs.
So this first light from EZI, it feels like more than just a technical step. It's like opening a new eye on our upper atmosphere.
It really is. We're getting a view into these powerful invisible currents, this magnetic connection to the sun in a way we just couldn't before.
Illuminating something that was always there, but kind of in shadow.
And that illumination is vital for practical reasons, too, protecting our technology, like we talked about. Better forecasting, better mitigation for space weather.
Yeah. So, thinking ahead, now that EZIE can map these currents in such detail, what's the most exciting potential discovery for you? Like, what unexpected thing might it show us about how Earth's magnetic field handles the solar wind?
That's a great question. I think understanding the really rapid small-scale dynamics, how does the energy cascade down? Where are the real hotspots? Maybe we'll find structures or flows we didn't even predict.
Could it change our basic models of how magnetospheres work?
Potentially, yes. Especially how energy couples from space into the atmosphere. It might refine those models significantly, or even, force us to rethink some aspects. And that deepens our appreciation for just how dynamic and interconnected this system is.
Beyond just protecting GPS signals, it tells us more about our place in the cosmos.
Exactly. Fundamental science alongside practical applications.
Well, this has been fascinating, and if you listening want to explore more, NASA's work is just vast.
Oh, yeah. From Hubble and Webb looking outwards to missions looking back at Earth's air quality.
Or even ways for people to get involved directly with citizen science projects.
There's always something new happening, always more to discover.
Definitely worth checking out. Thanks so much for breaking down EZE for us.
My pleasure. It's an exciting time for heliophysics.